Let us talk about insertion sort. Insertion sort is a simple sorting algorithm. Like bubble sort and selection sort, it's very easy to write the code, very simple to understand. But like those algorithms again, it's a quadratic time worst case. That's not the best possible time for a sorting algorithm. There exist sorting algorithms that sort an array in big O of n log n time. Algorithms like merge sort and quick sort, they take only big O of n log n time sort this array, and it takes quadratic time. We are going to study merge sort, quick sort in the upcoming videos. The next important point about insertion sort is it is in place and stable. So what do we mean by in place? In place is typically defined this way, that an algorithm is called in place if it does not use any auxiliary array or any auxiliary space in terms of input size. However, there are other definitions, like there are algorithms like quick sort which are called in place, however they use recursion called stack. But here insertion sort takes big O of one auxiliary space only, it does not take any space even for recursion, nothing. So it takes only constant number of variables. Stable. Insertion sort is stable. You discussed stability earlier. So what is stability? When you have two equal elements, their original order is retained. Let's now see the next point. Insertion sort is the most popular and the most efficient algorithm for small sized arrays. When you have small sized arrays to sort, insertion sort is always preferred. So there are sorting algorithms which are used in standard library functions. For example, Python uses timsort. And timsort, what it does, it uses merge sort, which is an n log n algorithm for sorting for general purpose arrays. And when your array is small, or when you are doing merge sort and array size becomes small, it switches to insertion sort. So insertion sort is used in these hybrid algorithms, timsort and introsort. Why am I calling these hybrid algorithms? Because they use 2 or 3 sorting algorithms together. For example, timsort uses merge sort and insertion sort. Introsort uses heap sort, quick sort, and insertion sort. And these both algorithms use insertion sort when your input is small or when input becomes small. Insertion sort requires big O of n time in the best case. And interesting thing about insertion sort is best case happens when your input array is already sorted, and the worst case happens when your input array is reverse sorted. Let us now talk about idea for insertion sort. So what we do in insertion sort, we maintain a part already sorted, right? And when we are at current element, we insert this current element into the already sorted part and we make the sorted part bigger. So when you are at index I, your elements from 0 to I minus 1 must be already sorted. And what you do with element at index I, you put it at its correct position and you increment the sorted part from 0 to I minus 1 to 0 to I. It increases by 1. So see, when you have an input array, the single element would always be sorted, right? First element is only, so there's no point of doing anything about it. It's a single element. So we begin with the second element, and what we do, we try to put it at its correct position in this subarray, right, from 20 to 5. So 5 goes here. Then we come to 40, 40 is already at its correct position. Then we come to 60, 60 is already at its correct position. Now when you come to the next element 10, see, this part is already sorted from 5 to 60. Now you want to insert 10 at its correct position in this subarray 5 to 10, right? So where will you put for 10? You will put 10 here, right? So you put 10 here and this part becomes sorted, right? Now you come to next element 30. So this whole subarray is sorted, only 30 is left to be put at correct place. So you put 30 at its correct place and 30 comes here and your whole array becomes sorted. So what we are going to do, we are going to run a loop that begins with the second element, because first element is already sorted, right? So for second element, our I is going to begin from 1, right? Now we are going to consider this 5 and we are going to put it in the sorted subpart or prefix subarray from 0 to I minus 1, which is only single element. And once 5 is placed there, we are going to do the next iteration for 40, right? And we are going to put 40 at correct place, and I equal to 3, I equal to 4, and I equal to 5, right? After I equal to 5, we get this array sorted. So this is how we are going to run a loop. Now it's still not done. There is slight complication. How will you put this element at correct position? These are simple array operations. You need to simply insert an item. So please pause this video and try to write down insertion code yourself. Now you have the complete idea, right? You are running a loop from I equal to 1 to n minus 1, n is the size of the array. And at every index I, your array from 0 to I minus 1 is sorted. and you just need to put this element at correct position here, and your sorted part increases by 1. Here is implementation of insertion sort. We have a function that takes an array and size of array as an argument. If you're programming in Java, then you can get the size by doing array.length. So what we do inside this function, we run a loop from 1 to n minus 1. So for this array, the size or n for this array is 6. So we are going to run a loop from I equal to 1 to 5. So what are we going to do in this loop? We are going to begin with I equal to 1, which means this element, and we are going to go till n minus 1. And for every element, we are going to first store it in a variable key, and then we are going to go to its left side and we are going to find its correct position in the sorted array, right? And once we find the sorted array, we increase the sorted array part, right? That's all we are going to do in every iteration. So key is initially part of unsorted, and after this iteration for I, this becomes part of sorted array, right? Our sorted array is going to increase. We are going to maintain sorted and unsorted. So when unsorted array is of length 0, your array is sorted. So when key is 5, right, you begin with I equal to 1. What you do is you want to put it at its correct position, right? So you want to make this sorted part is 520. For that, what you do is you go to the left side and you run a loop. You run another loop from I minus 1, and this loop will run while j is greater than equal to 0 and array j is greater than key. While key, while key is smaller, then only you will run this loop. As long as you find an element which is smaller than key, you will stop. We can better understand by this iteration. See, I is currently here. So what we do in this iteration, we begin from here and we go to the left side and we keep running the loop while elements are greater than the key or key is smaller. So we run the loop for 60, 40, 20 and we stop here, right? We stop at 5. And while we are running the loop, we move all the elements one position ahead. So we move 60 here, 60, this element becomes now 60, right? And since we are going to overwrite it, that's why we have stored it in a variable key, right? Now we move 40 here, now we move 20 here. So these two elements, they both have 20, 20 now. And after this iteration is over, at this location, we are going to write 10, right? That's what we do. At ARR j plus 1, we write 10 because our loop stopped when j was here, right? For 5 it stopped. So we're going to go here and we are going to write 10 here. That's what we do inside this loop. Same thing happened with this case. When I was 1, there is only one element. So we run the loop once, right? And then j becomes 0, right? Negative actually. So we come out of the loop, j becomes minus 1. And what we do after that? We write 5 here, and before writing 5 here, 20 must have been written here by this loop, by this iteration, right, in the single iteration. So this is how this inner loop works. It moves all the greater elements one position ahead to create a space for the new key to be inserted, right? And then after the loop, we insert the key at the created space. And this is how we sort the whole array. Let's now quickly see those cases as well when array I is greater than left of it. See, for example, here 40 is greater than 20. So we don't go inside this loop. And what will happen in this case? See, j is I minus 1, right? And since we do not go inside this loop, we do array j plus 1 equal to key. So 40 is going to overwrite itself, right? Same thing will happen here. 60 is going to overwrite itself. Now let's quickly talk about this condition also. Why don't we have equal to sign here? See, this logic will still work if you have equal sign, but then this algorithm will not be stable. By keeping the greater sign, not considering the equal sign, we make sure that the algorithm is stable. See, there was say 2 occurrences of 5. Say this element was also 5, right? So what will happen? You will stop here. You will not move this 5, right? Because this has come earlier. That's the advantage of not putting equal to sign. This algorithm remains stable. That's why we say insertion sort is stable. If I put an equal to sign there, then it won't be stable, because in that case, if there is a 5 here, then this 5 is going to come here and this 5 is going to move one position ahead, right? It will lose the stability. Let us now talk about time complexity of insertion sort. Time complexity of insertion sort in the best case is theta n, and in the worst case is theta n square. And in general, we can write it as big O of n square, right? Big O of n square covers both theta n square and theta n, because big O means upper bound. Let's now see how it's big O theta n in best case, and when does the best case occur? Best case occurs when your input array is already sorted. For example, your array is 10, 20, 30, 50. What happens in sorted array, you never go inside this inner loop. When you run for I equal to 1 in this example, your key is 20 and previous element is smaller, right? So you will not go inside this while loop. Same thing will happen for 30, same thing will happen for 40. You will never go inside this loop because this condition will never be true. So what you will be doing, you will be overwriting every element with itself. 10 will overwrite itself, then 20, then 30, then 50. And that's all is theta n work. You are doing constant work in every iteration, overwriting the element with itself. So the time complexity is theta n. Let's now talk about worst case. Worst case happens when your array is reverse sorted. What happens in reverse sorted is you are doing maximum shiftings in every iteration. When you are here, then 50 will shift it here, right? And you will have, after placing 30 here, you will have 30, 50, and then 20, 10. Then when you come to this element, right, 50 will be shifted here, then 30 will be shifted here, because both are greater than 20. So your array will become 20, 30, 50, and 10. And when you are here at this element 10, again maximum shiftings will happen. You will be shifting all three of them. So your array will become then 10, 20, 30, and then 50. So you are doing maximum shiftings. And how many shiftings you do for I equal to 1? You do 1 shifting. For I equal to 2, you do 2 shiftings. And you are going to run a loop from 1 to n minus 1. So you are going to do 1 plus 2 till n minus 1. These many times your inner loop is going to run and shift the elements. And this is n into n minus 1 by 2. Right? The summation of natural number formula for n equal to n minus 1 is this much. So this is clearly theta n square. We can ignore the lower order terms. We can ignore the constants. So we get the time complexity is theta n square in the worst case. And so we can write in general as big O of n square. That covers both of them.